Hello guys, good evening. My name is Mohammad Sabir. Today I am here with you. In these sessions, we are going to start a optimization method. Basically, this subject comes under the designing part. What basically we are learning, in a like when we deal with the designing problem, like machine design problem. Basically, in earlier uh, discussions, we basically we always try to find out the dimensions for a particular conditions. But in this case, how to optimize this dimension, like how to optimize the objective functions. Okay, uh, particularly in these sessions, we are going to discuss some method which is used to optimize the objective functions. These methods are applicable for multivariable. Okay, and like how to optimize the multivariable problem, how to minimize the problem. In context, the first method is steepest step. Basically, this is the steepest descent method. Okay, what basically in this method we do, basically we have objective functions like fx1 2. First, what approach we will follow in this sessions. Basically, we will learn by using examples, like what algorithm we should follow. Okay, basically this is a objective functions. Simply this objective function something like basically it's a mathematical kind of functions, but when you deal a practical problem, it's kind of a function of like strength, and there are a lot of steps. There are a lot of dimensions is will be there, so accordingly you can deal with it. But for simplicity and for to study and to learn the method, that's why we are using a simple x1 x2 variable, and we take a objective function x1 fx1 2 is equal to what, x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 raised to power square. Okay, and first in this method what we do, basically first we find a gradient matrix. Like how we find the gradient matrix, basically we find to find out this matrix, we have to calculate the delta partial differentiation of function with respect to a particular variable, a specific variable, delta f1 by delta x1, delta f by delta x2. Okay, in next slide we basically calculate a Hagen matrix. This is a basically Hagen matrix, you can see. And s1 is what, S1 is what? S1 basically like we you know what a gradient gives. A gradient gives like if anyone asks from you what basic uh, gradient gives. A gradient gives a like the functions where the like what basically gradient gives, it's actually in the direction of a maximizations. You can say like we want to find out like where a functions is going to maximize. Okay, for that case we have to find out the gradient. Basically gradient vector gives that directions. Okay, but now our purpose is to minimize the objective function. So what direction we have to use, that is minus del f. Okay, now we move into the direction of a minimizations. Like x2 is what, how to find the new iterative point. X2 is what, x1 plus lambda s1. You can see like this are basically a 2 into 1 cross matrix. Okay, 2 into 1 matrix. And basically we by using this lambda, we basically convert a multivariable two variable problem into the single variable. Okay, and then put a value into the main objective function and apply a single variable optimization method, and easily you can find out the optimized point. This is the first method. Okay, now we move to the second method. Basically, the purpose of this class is to a basic, like to give a brief idea and like how to approach the problem, how to like which method we should follow. And after this class, if you want to take if you want to do a practice, so we can also arrange a practice sessions for that problem. But now in today's sessions we only discuss the methods and like what difficulties you will follow while solving the problem. Okay, that's a basic thing. Okay, now move to the Newton method. Basically in Newton method, what we do for quadratic, if the equations, if the objective function is quadratic, then we find a iterative next iterations xi minus inverse of the Hagen matrix. And del f is what? It basically a gradient matrix. Okay, if the matrix is, if the objective function is not quadratic, then we follow a gradient, how to find the next iterations xi minus lambda Hagen inverse of the Hagen matrix and del f. It's a so simple method. Basically, by using lambda, we convert a double variable optimization problem into the single variable, and then we apply a any like there are a lot of methods. One of them we can apply into that, and we can find out the optimization point. Okay, next we move to the how to deal with a constant problem. That's very important. I think in operational research you have studied like how to deal with a constant problem, like linear constant problem. But now we are dealing with the non-linear with constant problem. Okay, like how to solve these problem. Okay, basically to find out a solution of this problem, we have to follow a optimization method. There are a lot of methods. In next later we will be discussing about those methods. Okay, now move to the first we have this simple question. I think this is visible. And fx1, the function objective function is what? X1 raised to power square plus raised to x2 raised to power x2 raised to power 2 minus 11 raised to power 2. This is a basic objective functions. This is a g x1 x2 and g2 x1 x2. This is the first constant, this is the second constant. Okay, then we will move to the, we have a 4 point. This what basically they tell. Basically these are the some random point. These are the some random point, but accordingly, we we will try to move into the optimized directions by using, we have some conditions, and we check, we will check it, okay, which conditions, which point follow these all conditions. And if else, anyone point, uh, if point which is which basically not follow the these conditions, we have to reject it. And the remaining point, whatever remaining point we will have, basically we will take as a optimized point. Okay, what basically in these sessions, just kind del f is what? Del f x1, del f x2. Okay, first find a delta f, then find a delta g, because delta f, delta g, and these all are the 2 1 into 1 matrix, 2 cross into 1 matrix. Okay, basically these are gradient matrix. Okay, now we move to the KKT conditions. We have to check these conditions, whatever point uh, we are selecting, basically it must follow these conditions. It must follow these conditions. If like if else like a point which basically will not follow anyone uh, one of these conditions, basically we have to reject it. Okay, first is what is first, we have a first condition, Kakati conditions: gradient of delta f minus u1 delta g1x minus u2 delta g2x. What basically we are doing, basically we this is the gradient of objective functions, and u1 the gradient of constant, minus u2. Why we use a minus? If the constant having greater than 0, then we use a minus. If constant is less than 0, then we use a plus sign. You you have to keep in your mind. Okay, this is a basic Kakati conditions. First, what we will do, first we write a basic gradient of objective functions, and then multiply with a constant into multiply multiply constant with the gradient matrix of a constant. Okay, accordingly you can write this first conditions, and then uh, we will move further, and this is what: g1 greater than 0, g2 greater than 0, g3 greater than 0, g4 greater than 0. And then we also have to check these conditions: u1 g1 x is equal to 0, u2 g2 x is equal to 0, u3 g3 x is equal to 0, u4 g4 x is equal to 0. What basically we have to, like if any point, any point follow these all conditions, we are adding into the optimized solutions. Okay, like with this point, this point can be taken as a optimized point, probabilistic, probably optimized point, we also can say. And this is the basic thing. I think you look into that. Now we move to the this is the basic method. Now we move to the how to solve a equality constant problem. Okay, basically a simple kind of thing you can easily like the first method is what basically we have a m, we have a n variables. If we have a m equality constant and n variable, easily we can uh, convert into the n minus 1 n minus m unconstrained problem. Okay, unconstrained problem. And then we can use a uh, multivariable optimization methods. Okay, then we come to the this is a simple rule. Okay, like how to identify that key, this problem gives maximization and minimizations. Easily you can find a Hagen matrix, and if eigenvalue of Hagen matrix is all eigenvalue of Hagen matrix are positive, then we can say this is a problem of minimization. If all eigenvalue of the Hagen matrix are negative, then we can say this is a problem of maximizations. Okay, now we now we will move to the complex search method. Now we move to the complex search method, like how to solve the multivariable problem by using a complex search method. Like we have a problem, this is a like this objective function is given basically, and constant is also given. Like a first, what actually we have to do in this problem, basically we have a 4 point: x1 x2 x3 and x4, 0 0 x 1 1 2 3 and 1 2. The first thing you should keep in your mind, first, uh, the first point which we are uh, which we are taking must be feasible, okay. Then then we go to the next point. This is a one. If this point is feasible, and it's okay. If it's not feasible, then we have to make a feasible by using this simple method. Like how to make this point feasible. Like x new is what, like this is a x new, and this is a x old plus half x old minus x centroid of remaining 3 points. Like if we take a first point and then we go to the second point, if the second point is infeasible, then we take a first point as a centroid. If the first 2 points are feasible and the next third point is not feasible, then uh, take a we take a centroid of remaining two point, okay. And then by using them we can find out the x new, and then uh, we have to check this is feasible or not. If we, even it is not feasible even it is not feasible, then you have to reiterate. You have to you have to follow again and again this procedure till until unless you get a feasible point. And then this is a so simple process. If we get a 4 feasible point, then find out the value of function on these points. Like we have these 4 values, and pick a maximum worst point. Pick a worst point, basically like in this case we have x1 is the worst point. Now we have to find out the xm. How to find out the xm? Xm is what, is the centroid of the remaining 3 element plus alpha. Alpha is given, basically is it basically a uh, like you can say expansion coefficient, okay. And like xc minus xh, xc is the centroid, xh is the worst point. By using them we can find out the xm. Okay. And we have to check this xm lie within the boundary or not. Like if in questions this condition is given that okay, x should be lie in between them. If this point is on out of the boundary, then we take a boundary point, like we take a boundary value as a xm, okay. And then you have to again check this point is feasible or not, okay. If this is not feasible, if it feasible, and okay. If it not feasible, so please try a please follow a previous process which basically we did for the uh, we did to make a feasible, okay. Now we come to the, like if we get xm, okay, and this is feasible, and then we find a function value. This is the function value, and you have to ensure that fxm should be must be less than f maximum, like worst value, okay. It is if it is not, then we have to follow this process. Xm dash is what, xm plus half xm minus xc, okay. And do iterations until you get uh, our desired value, okay. Then how to take a randomization in, like how to select these point in a random manner. In a first case, you can see that r1 is what, 0.1 plus 0.15 These all are the random numbers, and R2 is what 0.4 into 0.7, R3 is what 0.9, 0.8, R4 is 0.6, 0.5. We also have the condition for a uh, range of x1 and x2. This basically lies between 0 to 5. By easily you can find out that 0 plus is a first component of random number, low plus random number component, high minus low. Okay, easily you can find out the x1, x2, x3, x4 and follow a process as earlier we have studied. And then move to the linearized search method. In this method, what basically we are doing, basically we are trying to make a objective constant unconstrained. We are going to the convert into the linear forms. If you can see, this is the this basically non-linear objective functions. By using a Taylor series, we will try to make a linear. Okay, first, how to make a linear. The first, how to make a linear, this is an objective function. First we find a like we one initiating point is given. Find objective, find a function value at that point, plus 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 and transpose of a gradient multiply with x minus x naught. X minus x naught, it basically you also can visualize it, fx naught plus the gradient, the transpose of this gradient matrix, del fx1 plus del fx2, x1 minus x naught component of the first component of x naught, x2 minus second component of x naught. Accordingly, you can convert this problem into the linearized form. And after converting this problem, you can solve this problem by simplex and graphic graphing method. There are a lot of methods you can easily follow. So, okay, now we come to the Lagrange multiplier. Okay, this method is only applicable for the equality constant. Okay, this is so simple method. First, basically we have a objective functions. We have to minimize it, and there are a lot of constraint. Gx1 is equal to 0, gx2 is equal to 0, gx3 is equal to 0. Then what basically we do, basically first we write a Lagrange multiplier, you can see in the screen, f x1 x2 plus lambda g1 x1 x2 plus lambda 2 g x2 x1 x2. Okay, you can write it, and then find a conditions for that, find a partial differentiations of corresponding to each variable, and like put uh, equal to 0, and uh, when you solve this all equations simultaneously, you find basically a relations. You can find out a relation between uh, relation among them, and by using them you can convert this multi-variable problem in a some kind of a single variables. Okay, easily when you do calculations, easily you can understand this. Okay, how to deal with the non-equality constant. Okay, if you know, this is for the equality constant. Now we are going to deal with how we use this method, Lagrange method, for the non-equality constant. Okay, basically to convert a non-equality constant to the equality constant, we have to add the we have to add the slack variable. This is what, like g I xn plus vi y I is to whole square is equal to 0. Okay, then accordingly you can write it. Okay, now like how to solve these problem, like in this problem basically we get a three condition. This is very important, we have to look into that. We have to look into that. Basically this is the lambda x1 xy lambda fx plus lambda gxy. Basically the capital G is the function of both g and y. How we can write it, like you also can see fx is what, fx plus lambda gxy is equal to lxy lambda. Delta L by delta y is what? 2 lambda j yj is equal to 0. Delta Ly delta y is equal to 2 lambda j yj is equal to 0. And if we write, okay, easily you can see that, like when we partial differentiate with respect to a variable y, then we get a 2 lambda j yj is equal to 0. If a lambda j is 0 and yj not is equal to 0, then a lie solution basic inside uh, lie in the feasible regions. Okay, if the y is equal to 0, the solution at a boundary. If y is not is equal to 0, you can say solution lies in the feasible regions. And if both not equal to 0, then you can say solution is, we cannot take these solutions. Okay, we cannot take these solutions. Okay, then we move to the penalty method, like how to find the optimized point by using a penalty method. This is basically a phi x is what, fx minus r upon gx. This is the interior penalty method, which basically is used for feasible reason, and exterior penalty method it also valid for infeasible points. Okay, if phi x is what, like in interior penalty function, we write like how to modify the function fx minus r is the penalty factor, and upon gx minus 1 upon gx. Gx is what, it basically a constraint. And then in case of exterior penalty method, we convert a phi x is fx plus lambda maximum of 0 g uh, gx raised to power 2. What basically we are doing basically in the penalty function method, basically we are adding a large value in the objective functions. Like we are we are adding the contribution of a constant within the objective functions. Accordingly, the objective functions handle the, like you can even visualize it, like how we are approaching. Basically, we are adding the constant within the objective functions, and when we go to find the solution, basically like we can get mix up solutions. Like in this solution, basically the constraint factor is also there. Okay, this is the kind of algorithm. Okay, this is the Rx in this method. Basically, you have to, for interior penalty function, This is for exterior penalty function. Fx is plus lambda maximum of 0 gx raised to power 2. In this problem, basically, first we start from a high R value, and in case of exterior penalty method, we start from a low R value. Okay, and basically, back to back, we solve a same value, and like when we change a R value, basically, if we get a two same value back to back, then we have to change R value. Like how uh, we solve these problems, like please take example. It's like we are giving a flavor of it. K x r phi x fx fx phi, first derivative of phi x and second derivative of phi x and x new. Like easily, next iteration, how we find the new point, the x world minus phi 1 x upon phi second x, like first derivative of phi x upon second derivative of phi x, and then go and then check it ki like these two consecutive point become same or not. If the same, then we move to the next R value. Okay, next R value, and when we stop this algorithm, if the value of phi x and fx becomes nearest to same, then we have to stop this algorithm. Okay, this is just a simple procedure. Okay, thank you, all the best. If you have any doubt, you can ask